I'm Ramnivas. I'm going to talk about putting Scala.js in production. So for last three and a half years back, since last 3.5 years, we have been working on a product which is completely written in Scala, front-end and back-end. And I want to talk about experience making such a large application work, and we launched it last week. So what was that journey like? What lessons we learned and what lessons you can apply in your own product. So before I jump, the product itself is called Learn Raga. So Raga is a basic melodic form in Indian classical music. So it basically describes what notes you can use, what are the ways you can use notes to create music. But the ultimate goal is to create a particular emotion. So there are ragas for happy, joy. There are ragas for melancholy mood. There are ragas for just being upbeat. And there are also ragas for different time. I'm a student of Indian classical music. I play flute. The issues I faced during trying to learn this music is what motivated us to bring this product. So you can visit today at https://learnraga.com, and you can sign up and try to understand what we do about it. All right, so let me, before I jump into it, I want to bring out the relevance of this product. So I just looked at our GitHub commits, and we got like almost 3,000 commits. It's a very small team, 3-people team. And a lot of refactoring happened as we learned more about how to model this music. And this is where Scala came into picture quite a bit. So our 90%, almost 90% of code is in Scala. Other is HTML, a little bit of JavaScript, and actually JavaScript is just 0.5%. And I don't think we could have succeeded without actually Scala.js, especially static typing part of Scala.js and functional programming part of Scala.js being available to us. So before I jump into other part of presentation, let me give a quick demo of the product itself. So this is the site. Let me log in. So it basically gives you like the front page, as you expect, gives overview of what you can do with this thing, what are the possibilities here. Let me log in. So one of the core idea in Indian classical music, and like many other music actually, is a composition. It's a pre-written form of basic melodic pattern, which you are supposed to play, grasp it, and then improvise on top of it. So what I'm going to do is I'm going to actually find an interesting composition in rag called Kalavati. This is actually more an evening melody, but never mind. So this is the composition, how it looks. It's a spreadsheet-like environment. And these notes you see are like essentially are telling you which note to play. So these are like, I won't go into detail. Like it's do, re, mi. There is a similar system in Indian classical music. But entering these notes can be very hard. Like you can see like there are sometimes underscore here. Sometimes can be a dot above, which represents higher octave. It can be dot below, which represents lower octave, and so on. So what we offer first thing is we offer a simple interface where you can type in notes as simple as by going to piano and typing in notes. So that's the first one of the things we do. Second, given this, it's an editor-like environment, we want people to allow undo, redo, that sort of thing. So I will undo this, and those notes are gone. You can also like select a particular notes, move them, delete them, copy, cut, paste, etc., etc. So I won't go into all the features, but essentially, it gives you all the things that you would expect from an editor. It's a composition, so you can actually play it. So let me try to play it. That sound is because of I'm playing through Soundflower. Originally it plays pretty fine. So you can play compositions, and general idea is you will go take this composition and put it into a repeat mode and keep playing it as you need. So next one we do is we also allow people to practice this particular pattern. So for example, in this case, this pattern is like 1, 2, 3. So if you play this, can I get the microphone?
Try on the left side.
Yeah. Can you hear? And this idea is, when people learn this music, you take this pattern and practice them for like hours at a time, and you keep changing patterns. The idea is to really understand and learn how to switch from notes, one note to other note in a correct form. And finally, and in this case, for example, one thing we offer is pitch detection and other things, but I will come to that part a bit later. We also offer this something called practice room, which basically gives you an accompaniment instrument. So now you can play it, improvise it without actually having a melody in front of you. So let me switch back to presentation and talk about it, and we'll come back to this demo a bit later as the things go along. So why did we use Scala.js? First of all, it's Scala. I'm comfortable with Scala, and all our founders for this product, they are all comfortable with Scala. We like it because it's statically typed, it offers functional programming. It's a fairly mature ecosystem, so pretty much any task you want, there's a library for that. You can use that library. It's also good. It offers good interoperability with JS. So let's face it, right? A lot of components I'm using, those components aren't like something that I need to write it from scratch. Somebody has written. There's a library out there. I want to use it as is. So I can just take those libraries and use it from Scala.js. So I don't have to write every single line in Scala. It also supports isomorphism. So isomorphism is essentially ability to do it something on server or client. So people use it, for example, to render web pages on server side and then give it to or render pages on the web in browser. We use it in a slightly different manner. We do it to share code between JavaScript and JVM. So by actually having most of the model that is workable in both JVM and JS, we can really gain good productivity by running most of the time developing, debugging everything in JVM, and then when time comes, we test it in the browser. And almost always, everything just works. We have not found any problem where code worked in JVM but did not work in JS. We also use React. So, React is a framework for writing web applications, and it's very popular, pretty much these days, default framework to do any web development. It's by Facebook. It's pretty mature. It's very widely used. Like Scala, it promotes immutability. So most of the time, you will be writing code such that you will feel very familiar. You are essentially making transition from one set of application state to other state. And you don't go and change and then expect Vue to reflect that. Also, React works on multiple platforms. We right now deploying on web, but it also works with native, and if we ever want it, maybe even virtual reality. Roughly the way React works is you have application state, S0, and you have some function, transformation on that state to get a view, V0. So, and now if you want to go and make some changes, so basically a network call comes or user interacts with user, types it in, then you are making a transition from state 0 to state 1. And now you apply the same function, which is state to view transformation, and then you get a new view. But if you do it very naively, then you will be rendering page, and then something changes, and you are going to render the whole page again, and that's going to be pretty bad user experience. So what React does is it finds out the difference between these two views. So in fact, the way it renders it is actually renders into something called virtual DOM. And those virtual DOM, it finds a difference, saying, okay, maybe I need to update only this text field. And it only updates that particular field. And it does through DOM mutations. So it basically gives you that experience of going from one state to other state, and overall feel of immutable application state, but without actually associated performance penalty, if you were to do it naively. React's component model has two parts. One is properties and other is state. So if you look at a top level component like this, it will have a property PA and state. And then you will have a component tree with subcomponents that will take its own properties. And it will also, that property will be typically passed down from its parent component and so on. And each of the component may have a state. There are two kinds of components, stateful component and stateless component. So they have a state, they will have it within themselves. So states is not something exposed to the outside. Property is a way for parent to communicate to the child, and state is a way to keep some internal state without exposing it to the world. And then so on. So every time you go, you keep passing it along, those properties, some transformation of properties and state to your children, and children in turn may have their own state. So coming to the production, we want to utilize developer skill set. We want to basically do such that, if you want to work with interns or hire people, then we want them to be productive immediately. So what does that entail? One is writing web application requires a combination of skills. It's actually pretty hard. Writing web application is, these days, especially with a single page application, is as hard or even harder sometimes than backend application. In our case, it requires knowing Scala, knowing functional programming, knowing JavaScript, knowing CSS, and all the ecosystem around all these tools. So what we do is, solution is to use the tools and frameworks that match JavaScript world. That way, if somebody understands the JavaScript world, because most of the UI developers are going to be familiar with JavaScript. So use those skills and by using the same or similar frameworks. So what do we use tools-wise? We use Webpack. So if these days, if you want to take JavaScript, your JavaScript code and deploy it on to a browser, Webpack is the way to go. It's another de facto standard that everybody uses. So it basically allows you to essentially gather all the assets, CSS files, images, HTML files, JavaScript, everything, and puts it into a bundle form, essentially a JavaScript package that serves everything. From Scala perspective, obviously we want to use tools that are familiar to Scala developers, which is Scala.js plugin, because we want to compile Scala code into JavaScript, and Scala.js bundler plugin, which essentially drives Webpack. So rather than using Webpack directly, which we used to do earlier, but since Scala.js bundler is available, we switched to using it through that. So you don't actually have to start one Webpack and one SBT. You just start it from SBT itself. We use a framework called Slinky, and Slinky is developed by Laddad, who is here. He's my son, and so therefore it's like a homegrown framework for us. We can't say not invented here at all. All right, so the idea behind Slinky is if you know React and a bit of JavaScript and Scala, you can be effective with Slinky. You can get started in a few minutes. In fact, Slinky offers template, so you can do SBT new and the template name for Slinky, and within couple of minutes you will have a Slinky application running, or same thing for React Native. So you can have an iOS application or Android application running in a few minutes. It offers direct mapping of React concepts. So if you know React and you look at Slinky code, Scala code based on Slinky and React code based on JavaScript, you will almost feel like this. It almost looks the same, with of course obvious differences between the two languages, which are not many actually. If you look at modern JavaScript, except for types, it basically looks the same as Scala. It also offers great support for external components. As I mentioned, we want to leverage the ecosystem as much as possible. So if there is a component out in the wild, we want to just take it in, use it from our application. So Slinky using external component is very easy. It also keeps up with new features in React. React, if you look at like last 4 years how React evolved, it's pretty dramatic. They started without actually having React class. So you define in a kind of different way. Then they started to use ES6 classes. And now they are kind of going with functional components, and now they're going back to something called React hooks. So it's like it changes every year. Basically, if you did not pay attention to React, in a year React will look very different. Conceptually same. So idea is exactly same. The picture that I showed you earlier of taking component tree and having state properties getting mapped down to children, that remained the same. But the flavor, the syntax, that changes every so often. So Slinky keeps up with these features, and that's awesome, because then we get to leverage whatever is new coming in React. So this is how a typical component will look in Slinky and React style. So in this case, I'm showing a volume meter. When I'm detecting user's microphone, I want to show what is the volume like. So I declare here what are the properties I want. And so I have amplitude. I'm actually not using max amplitude in this case. I cut down code and forgot to take it out. But anyway, I have amplitude and max amplitude. And I want to render how should a volume bar should look like. So I basically put two divs, and the width of the inner div is proportionate to the amplitude. So and I give it a percentage. So basically volume meter will show. I'll show that when we give the pitch detection demo. And this one was a stateless component. There is no internal state. So essentially, the component is essentially a transformation of the property amplitude to a virtual DOM. If you want to hold on to some state, so in this case, the only state is it initialized. So in this case, the Google button that I logged in at the very beginning of my presentation, when you have the Google button, you need to first initialize the Google G API. So all that thing, you need to manage it. So you need to know that when to enable the button. Therefore, we have this initialized state. This need not be known to outside world, so we keep it as an internal state. And then we have the remaining code. Similar, this one is similar code in the sense it's rendering a button, but the disabled state depends on is it initialized or not. External components. So if I go, let me log out. So I have this here carousel. So these carousel surprisingly takes kind of quite a bit of, it becomes pretty tricky to do it right, do the right animation, everything. So rather than writing it yourself, I want to use a library called Slick Carousel. It has nothing to do with Scala Slick library. It's just called Slick. It looks slick, I suppose. So anyway, so using that component is very, very easy. So first three statements are essentially you are saying, I want to import those assets, JavaScript, CSS, etc. And the last is the only, and then there is you want to define some behavior. Usually React components don't have any behavior because you are not expected to use imperatively. You are not expected to say, go to the next slide or anything like that. You simply say, what is the current slide, and then it will figure it out how to get to that slide. But this particular component happen to have behavior. So in this case, I'm specifying that there is a behavior called go to particular index. Once you define all that thing, then you simply, then you simply define here slick carousel, and then all you define is a properties. Essentially, you take this original component, look at its properties, and map it into a type-safe form. And that's it, basically. You're essentially saying how should it look from the Scala world. And that means should it show dots, should it show arrows, is it an infinitely scrollable component, and so on and on. And then you're done. So you don't actually write a whole lot of Scala. Essentially, you're writing a binding between Scala and the underlying component, and that's about it. The next thing I want to talk about is extracting performance. So in Scala, we love, actually, let me talk about the problem itself first. Or you know what, let me give a demo that will make the problem very obvious. So I am going to play a recording and ask I'm going to play a recording. Actually, one of our music advisor, Nagaraj Hegde, that's his recording, commercial recording. And I'm going to see what kind of pitches he's playing. So let's do it, and then we'll talk about it. So this is afternoon melody. It's called Shuddha Sarang Rag. So these are the highlighted lines represents the note that are allowed in this raga to be held. So you will see that he will never ever stand on a note that is not one of those lines. There are actually faint lines in between. You probably are not able to see it. I will let it play for a minute. So here I'm drawing, detecting pitch, drawing everything at 60 FPS. Because if I do anything less than 60 frame per second, which is essentially update every 16 milliseconds, the chart looks very irritating. It looks like it's jumping at you and it's like you can't watch it for any more than a few minutes. So that becomes a challenging because you want to do record the pitch, detect the pitch, plot it, keep moving this chart at that particular speed. All right, so I will, as interesting as the music is, I will stop and talk about how we do it. So our task is to take microphone input, connect it to audio source, detect pitch, and then update the chart and do it at 60 FPS. So immutability is wonderful, right? You know, we like Scala often because it supports you immutability to the extent you want. It's very easy to reason about it because you don't have to say, well, I don't know if somebody modified my structure in between. You don't know, you know that, you know, okay, once you have created an immutable object, there is no way to modify if you wrote it correctly. And things like implementing undo redo functionality is like trivial. So initially I showed you, like I typed in some notes and I just did undo. Because the way we do it is, when we modify composition, we put a new composition in an undo stack. So we basically take the composition, update whatever it needs to be updated, as in a copy, put it onto stack, and keep doing this. So when it comes to undo, all we do is go back to the stack, and we're done. So there's not really a whole lot, you know, it's like a 10-15 line of code, and you got undo redo functionality. So it's all great, but if you overuse it, or if you don't use it right, then it affects performance in certain critical part of code. And in our case, it has been pitch detection and plotting and everything. So initially we did it without, you know, we tried to do essentially everything immutable, and it was horrible performance. And it wasn't, I should correct myself, it wasn't that performance was bad, it was the garbage collection. I would produce so much garbage because essentially we take a 4 kilobytes of frame every 16 milliseconds. We take 4 kilobyte of frame, we do DSPs, involves FFT, autocorrelation, a lot of other magic going on there. But fundamentally, and in that process, if we do that transformation, saying, okay, every step take signal, calculate FFT, take its square, then calculate its power spectrum, then take its inverse FFT, do other magic. If I keep immutability every step of the way, I'm going to create a lot of garbage very fast. So what we do is, we use mutability as needed. So keep it local or to a small subsystem. So when we, for example, in case of our FFT buffer, we just keep overriding it. We don't, once we allocate it, we just keep using it as needed. Now we don't leak it out of that subsystem, so we don't have to worry about it reasoning outside of the system. But within the subsystem, we just say, okay, you need to know that this is mutable data structure, use it carefully. And it works beautifully. That said, don't go and saying, okay, if something is slow, just let's go and make it mutable. It's not going to help you. Measure. So we basically went to Chrome, profiled it, and understood that, okay, this is actually a problem. Garbage collection is a problem. We can see actually where it's collecting garbage, and that time the chart just suddenly stops. and then say, okay, that seems to be a problem. Then you say, okay, what must be producing garbage? You measure that part, and then you go from there. Second part is if I use JavaScript. See, all this thing is running in JavaScript. It's running in browser. There's no backend involved when I was playing it. In fact, couldn't have because the network latency will just kill it. So I want to make JavaScript as performant as possible. And if I do, again, digital signal processing in JavaScript without thinking too much, I'm not going to get 60 FPS. So for example, if I do FFT in Scala in JVM, I get it within 3 milliseconds. If I do the same FFT in Scala, but run it on JS, it's about 14 milliseconds. And 14 milliseconds is already cutting it. I want every whole thing to happen at within 16 milliseconds. So if I give 14 milliseconds to one FFT, and then not even talking about inverse and all those things, I'm already out of budget. I can't update anything more than 20 FPS. So what we do is we do FFT in asm.js. asm.js is essentially is a restricted JavaScript format, which can be generated typically by compiling C into JavaScript. We are considering switching to WebAssembly, which essentially has the same idea. You write it in a language such as C or C++ or Rust. Essentially, right now, it doesn't support garbage collection. So as long as you write in a language that does not require garbage collection, you are good. Then second is, as I mentioned, React tree, whenever you change something, it goes and modifies all the subcomponents. It keeps passing on properties and state as needed, and the components are updated. Now, if you do it naively, then if you change something at the top level, potentially you are affecting the whole component tree. And yes, React will eventually find that, okay, the V1 and V0 and V1 happen to be the same, so there are no DOM mutations that are needed to run. But even before get to that point, it has to calculate V0 and V1. And then say, okay, yeah, that's the same text, no need to do anything. We want to avoid even that. So React offers something called shouldComponentUpdate. It essentially says, here are old properties, here are new properties and state. And do you think it's even worth calculating the view? So typically you would go and check if there are relevant changes that have happened. So when I'm, for example, in a composition, and if I'm selecting this text, for example, I want this pretty smooth, right? So I don't want to go and affect every single component. Could you even see actually? No, it's washed out. Okay, you can't see it, but essentially it's showing in a blue text saying it's selected elements. And to do this, you have to be careful because in theory you have changed selection. That means you are affected this part, you are affected this part, you are affected this part. And this eventually answer will be, well, there is no real change needed here. But what we do is, therefore, we write components such as this to basically say, has selection changed for this particular section or particular line or particular cluster? And then we minimize calculating those virtual DOMs as much as possible. The next challenge that you face is, yes?
Sorry, so you have to override shouldComponentUpdate for all components and aggressively tell them not to update, or you have to override it just for the ones that you have to be careful about?
All right, the question is, do you have to override shouldComponentUpdate for all components or the one that actually you think performance sensitive? Yes, only for performance sensitive. So typically you get a lot more benefit for doing it at higher level components in the tree, I mean. The reason is, if you could short circuit there, then the tree below that is not going to get evaluated at all. So then you get a lot of benefit out there. So what we do is we try to do as much work short circuiting as possible at the higher level component, but at lower level you get a little bit more benefit. By default, it will say should, yes, true, it should update because it doesn't know any better. Now with React hooks and other things, there are like more interesting way to express these ideas, saying, okay, essentially they have effects system where you can say, okay, these are the properties that are important for this particular update, and only if these properties are changed, then register as a change. And there's a whole system for that, but core idea still remains the same. So next thing you want to know is how to work with build time. So I'll go a little bit fast because I think I'm running out of time. So if you were to run test in JavaScript, you will see that even if I make a small change, in this case I actually made no change, but even going through the whole build process, building JavaScript, bundling it with Webpack, it took about 13 seconds. Same thing if I do with JVM, the same code, then it takes about 1 second. So when I'm developing, especially when I'm developing these DSP algorithms, I'm making lots of small changes, experimenting, right? I don't want to spend 13 seconds every single time. It gets boring, really, right? So what we do is we exploit this JVM JavaScript isomorphism to the maximum possible way. So we write most of a code such that it is shareable between JVM and JS. And normally during development we work exclusively on JVM environment. It's fast, we get it working. So even like some of the things that doesn't exactly make sense, we don't expect it to work from JVM ever. For example, selection. We have no business of doing selection from JVM. We don't expect it to be deployed in the JVM. Yet we write code such that it is testable from JVM, and we share it, and that really has been very helpful. That would be one reason I would say Scala.js you should use, because you can develop in Scala, run it in JVM, and once you feel good about it, you can use it. Also, of course, you get advantage where, like for example, these pitch detection algorithms, we often run in backend. Same code, no change whatsoever. Run in JS when we want to give real-time feedback. When we want to do analysis, we do it in the backend. And there's a full isomorphism. You have to, of course, deal with some JVM JS differences. There are not many, but all are related to things like HTTP. So you want to have, if you're HTTP, you have to abstract it out. So we can do it AJAX HTTP in JS world, OK HTTP, for example, or some other implementation of HTTP in JVM world. No deep ideas here. It's simply like have abstraction, have a trait, and have implementation that work the right in each environment. File system, similar thing. A little bit more interesting this one because there is no file system on JS side. So you kind of have to like create a URL-based file system, serve it from a local HTTP server, and use it. The last thing I want to talk about is bundle size. So when you compile all this code, user has to download this. So in our case, let me actually show. In our case, the overall bundle is about 780 kilobytes. So most of it is this is compiled with Scala.js, and these are the external libraries that we use: React, Braintree.js, FFT, and so on. It can be a problematic because user has to download. This is gzipped almost 800 kilobytes. So user has to download it, browser has to unzip it, parse it, and run it. And it takes time, especially if you're on a slow machine or slow network. So what do we do? But there's another tool, let me show you that. So this is basically tells you nothing about how JavaScript code is coming, Scala.js code is coming from. So there's another tool which is called source code mapper. It gives you a lot more detail. Doesn't look as fancy, but it tells you like, okay, my Laddad model is overall contributing about 7% of the code. If I look at my pitch, it's about 1.5%, and if I look at transcriber, it's 0.1%. So I can look if there are any hotspots. Unfortunately, for our case, there are none. So this is the size we are going to get. This is something that I think Scala.js could help us. So one of the things that we do right now, without Scala.js changes, is we use long-term caching of all assets. So once you downloaded JavaScript or CSS, then we do content-based hashing, and therefore you don't have to download it ever again until we change the version, of course. Trivial to implement using Webpack, and we are working on pre-rendering some of the pages. It does help with first meaningful paint. There are essentially two measures: first meaningful paint and first meaningful interaction, user interaction. So this will help with first meaningful paint. So as in, you will see the JavaScript HTML loaded because we would have pre-rendered it rather than you getting a JavaScript that will be rendering all components. You will get an HTML. It won't help, however, with first meaningful interaction. This is where we hope Scala.js is going to help us with something called code splitting. So the way people work in JavaScript is they write JavaScript, and each of the module require other modules, essentially dependency declaration. And then some of the declaration can be saying it can be loaded asynchronously. And Webpack, for example, or any other bundling software will take that as a clue and saying that those are the boundaries I can cut my bundles at. So for example, when I load front page, I can declare that all other pitch detection and composition editor and everything does not need to be loaded just yet. However, when I switch the route, when I go to composition, I can say, okay, now it's time that you should load it. Load it and then render the page. So essentially you are distributing this cost of bundle over in each view. And that's a much better user experience. Right now, Scala.js does not support it. It does not support code splitting or neither asynchronous loading. This is something hopefully we'll address soon. There are actually issues open, and that would be really, really awesome. I'm going to skip this part. Essentially, the point there is don't try to bundle JVM and JS code in one thing and serve it from one process. We deploy separately. One is JVM process, which does API, and there's a JS process, Node.js in fact, which just serves the static assets. That's very, very nice. We don't, in fact, sometimes restart the server for weeks at a time, because we are either working in a UI modification mode or changing server, so we only deploy that much part. Last thing I want to say is if you deploy as is, this is the kind of errors you're going to get in production. If you get a stack trace, it means nothing actually to anyone. It's basically what the way Scala.js does is it uglifies it, then Google Closure compiler. By the time you see your code, it's all gobbledygook. However, you can actually enable source map in production, and then you get nice call stack, which are like essentially giving the Scala line numbers. And when you click on it, actually you show the Scala code. And this is really awesome. But you don't want to necessarily expose your source code. So the trick to do is in your source map, you rather than serving it as is, you share it, you give some local URL or server that you control. And in this case, I'm saying load it from local server 10,000 URL. So that means somebody, people out in the wild won't get access to my source map. And giving access to source map is essentially giving access to source. All right, that's about it. I don't know if you have any time for question.
We do.
All right. Shoot.
Questions?
Yeah.
Have you encountered any difficulty interacting with common React libraries such as Redux or React and expressing objects and functions from these libraries with Scala type signatures?
Yeah. The question is, was there any difficulty in taking libraries such as Redux, which is popular in React, and expressing that in Scala? We don't use Redux. We did try experimenting with something called Diode, which is essentially Scala equivalent of Redux. There was no difficulty really, just that we didn't really necessarily wanted to express our state in that particular fashion. But as I mentioned, interfacing with external libraries is very easy with Slinky. It's really like, and Redux would be the same thing. So for example, we use GraphQL and we use Apollo. An Apollo client is written in JavaScript, but we can just write a facade for that, express our types in Scala manner. So when we use it, once we carefully describe those types in facade, then using it from Scala is very type safe. As type safe as we made our facade to be. Sometimes we get lazy and say JS dynamic, which is essentially saying anything goes, and that works then to that level, yeah. Any other question? Okay. All right, thank you.
Thank you so much for a great talk, Ramnivas.